In the next several examples, we're going to look at the limit as x approaches an infinity of a rational function. If we look at example 2, I'm going to work this one through all the way out in kind of great detail, and then we'll kind of discuss maybe a shortcut trick that you might have seen in a college algebra style course. Here we want to find the limit as x approaches infinity of 2x minus 1 divided by x plus 1. In order to find this limit, let's rely on the limit theorem we just found a little bit ago. And that limit theorem I'm discussing is the following. The limit as x approaches either plus or minus infinity of c divided by x to the r, where r is a positive rational number such that this expression is defined, c is a constant, this limit is equal to 0. The way in which we're going to employ this theorem is we're going to look at this rational function, and we want to divide every single term in both the numerator and denominator by the largest power of x that's found anywhere in the expression. Well, the largest power of x is kind of a tie. Both of these two terms are x to the first power terms. So the highest power of x that's anywhere in this expression is x to the first power. Let's go ahead and we're going to divide every single term by x. So there's my numerator of my main fraction, and here's what our denominator is going to look like. So we divide everything by the highest power of x, that's sometimes referred to as the dominant term. This is equal to the limit as x approaches infinity of, this will reduce, this gives us 2 minus 1 over x divided by 1 plus 1 over x. And from here, we can now use this limit theorem to notice that this limit here, as x approaches infinity, this piece will approach 0, and similarly, this piece will also approach 0. The limit of the other parts are just constant, so they exist, and then the quotient will have a non-zero denominator. So our final limit is going to be 2 minus 0 divided by 1 plus 0, which gives us a limit of 2. So for this function, the limit as x approaches positive infinity is equal to 2. We would have been able to notice that kind of a little bit more quickly in the very beginning. This is a very common thing that will happen when you have a rational function. Whether you're approaching positive infinity or negative infinity, it's not going to matter. If the numerator and denominator have the same highest power, then the limit will always be the ratio of those leading coefficients. The leading coefficient up top is 2, the leading coefficient on the denominator is 1, and that ratio is going to be 2. Let's take a look at example 3, part A. We want to find the limit as x approaches infinity of another rational function. We're going to do the same thing. Let's divide numerator and denominator every term by the dominant term. The highest power of x that appears in any one of these expressions is this x to the second power. So we're going to rewrite this by dividing every single term by x squared. We have 2x divided by x squared plus 5 divided by x squared, all divided by 3x divided by x squared plus 1 divided by x squared. We can algebraically simplify this. This is the limit as x approaches infinity of, we can cancel one of those, that's still going to leave us with a 2 over x plus 5 over x squared. Here, both of those cancel, so we're left with 3 plus 1 over x squared. We can now apply that limit theorem. As x approaches infinity, this term is going to approach 0, this term is going to approach 0, and this term is also going to approach 0. This other term is just a constant, so it's going to have the same value. It's not going to change. Until we see that in the limit we get 0 plus 0 divided by 3 plus 0, which is 0 over 3, which is equal to 0. So the limit as x approaches infinity of 2x plus 5 divided by 3x squared plus 1, that will be equal to 0. This trend will always occur, by the way, if you look at this rational function. Anytime the highest power of x resides in the denominator, it will always be that case that limit will be equal to 0. Let's take a look at part B. We could apply the same technique. We'd want to divide everything by the dominant term. The highest power of x is that x squared. If you want to, you're more than welcome to, and you're allowed to use the shortcut trick on this. Noticing that the same highest power belongs to both numerator and denominator means that the limit will be the ratio of their leading coefficients. So this limit will reduce to just 2/3. And if you wanted to justify that and show all the work, you would simply go through, divide every single term by x squared. You would have a 2 plus 5 over x squared. This would be a 3 plus 1 over x squared. This term would go to 0, this term would go to 0, and we'd be left with 2 over 3. We have one more case to look at. Let's see what happens with this one. We've already seen what happens when the numerator and denominator have the same highest power. We've seen what happens when the highest power is in the denominator. Now let's take a look at an example where we have another rational function, but the highest power of x this time resides in the numerator. Work-wise, we're going to take the same steps. I'm going to divide every single term by that highest power of x. So I'm going to divide every single term, both numerator and denominator, by x cubed. This is going to give us the limit as x approaches infinity. Here, these will cancel, so we're going to have 2 plus 5 over x cubed divided by, in the denominator, can cancel 2 powers with two of those. We'll also have a 3 over x plus a 1 over x cubed. Now, if we take a look at what's going to happen this time, according to that previous limit theorem, it's true that this limit's going to go to 0. This limit's going to go to 0. And this limit is also going to go to 0. So what would the overall limit look like? Well, it would look like this. 2 plus 0 divided by 0 plus 0, which is 2 over 0, which is undefined. So this time the limit is not going to be a real number because we get the expression 2 divided by 0. If you recall back to the section we've seen previously when we talked about infinite limits, especially as it pertained to things like vertical asymptotes, remember that when you have a non-zero number being divided by 0, that produces an infinite limit. Either positive or negative infinity. Recall, this is very different, however, from 0 over 0, which we talked a lot about. That was an indeterminate form. Whenever you get an indeterminate form, there's many different ways to kind of approach the problem to find the limit. It doesn't mean the limit does not exist. It simply means that whatever process you used did not directly produce and yield the limit. If you end up with an indeterminate form, then you should try to do things like algebraically simplify the function. You could go back and resort to a table of values to find the approach. Or, if you have a graphical approach, if you see the graph of the function, a lot of times you can determine the limit in that fashion. But non-zero over 0 means that this limit is going to be infinite. So, properly speaking, we could say that it does not exist, but let's be a little bit more detailed. Let's say specifically which infinity this limit is going to approach. If x is approaching positive infinity, then all of these inputs we're using for x are going to be positive values. So this quantity is going to approach 0 through positive values, and the denominator is also approaching 0 through positive values. What that implication means is what we're doing is we're taking 2 and dividing it by smaller and smaller and smaller positive results, which means that the answer is going to get larger and larger and larger and stay positive, so that answer will be a limit of positive infinity. If you don't feel comfortable kind of trying to work the analysis in your head, you can always just pick a value of x. Once you know it's going to be an infinity, pick any large value of x, 100, 1,000, etc., plug it in, and then if you get obviously a large positive answer out, then you would know that it's going to approach positive infinity. If you plug a test value for x in, and you see that you get a relatively large negative number, then that would indicate that that limit is approaching negative infinity.